Okay, so next example deals with force and pressure on a wall, or it could be on a dam, or this could even be the force and pressure that's pushing out on the wall of your fish tank. Okay, so the first fact we need is this idea of what's called hydrostatic pressure. Hydrostatic pressure. And what hydrostatic pressure tells us is that if you're at a certain depth h, then the force around you is constant based on the density, the force of gravity, times how deep you are. Again, h is the depth. The deeper you go into the water, the more force you're experiencing. That's why they need special machines to do deep sea submergence, right? Because the further down they go, the more pressure that builds up. And it's also why people that dive in a wetsuit to a very deep depth have to take their time coming back up to let their body adjust to the change in pressure. Otherwise, certain gases that get into your body can be a really big problem. You know, as you if you go up too quick and don't allow your body to adjust. But the force in every direction is based on just the depth and the density of the water that you're in. Okay, so force is the density times gravity times your depth. Now we want to use this idea that the force is based basically on the depth, since rho and g should be more or less constant in a body of water. We're going to use this now to compute the total force that's being exerted on some surface. That surface, again, could be a glass pane. If you're at a big aquarium, where you have hundreds of thousands of gallons of water in that tank, it's huge. How much force is being exerted on that window glass that you're looking through. Or if you're dealing with like a dam, water's up against the dam. Or really even the side of a pole, if you wanted to look at it that way. Or even just a simple little aquarium. So here we're going to be given some shape for our wall. And it could be as simple as a rectangle, or it could be some other kind of shape. Like here I have some kind of trapezoidal shape. And we want to be able to compute the total force that's being exerted across that window, across that surface. Like you said, like a dam or the wall of an aquarium, something like that. Okay. So what we do is, as we've been doing, is we subdivide. Okay. So we would subdivide this thing up into a whole bunch of little intervals. Right? A whole bunch of little intervals. So we're at some point here, y sub I. Okay. Right. And what we would do is we approximate the width here, right? We approximate the width because we can think of this as we let our intervals go to infinity. It's really just being a rectangle, right? Just simply being a rectangle. We have a length, and we have the height yi, right? And that's basically what we think of it as. It's just simply a little rectangle. So what we need is a width function. So we measure the width, call it w sub I. Right? And that width is going to depend on, I should just say w of y sub I, where we're currently at. Okay. And then we say, well, how much water do we have? Well, if we label the bottom of our dam as 0 and the top as A, then we'd have a height here of A, we'd be at a depth of A minus Y sub I. Right, that would be our current depth. And so the force that's being exerted, would be rho G. Hang on just 1 second. So I made it one little note. This is actually the force that's exerted on a body at that depth, which is actually called the pressure, which is actually the force divided by your surface area. Okay, so it's actually not the force, it's the pressure is the force that's being exerted on a body. Okay, so that's actually pressure. So now we're back to F sub I. It's just going to be the pressure that we have. Okay, rho G times the current depth, A minus Y sub I, times, how much surface area do we have here? Well, the surface area is basically approximated as the width times delta yi. All right, we figure out the surface area. That's how we get our total force for that segment. And then we would add them all up and get our overall force function, which will be the integral from the bottom of our tank to the top, or whatever, the bottom of our wall, however we want to do that, of rho G A minus Y times the W of Y function, the width function, times dy. And so now we have our function here that tells us the total force, all right, which is just taking the pressure, that's being exerted, times the surface area to give you the total force for the whole surface. And so this is kind of an important thing. If you're building a dam and you know how much water you need to hold back, you need to know how strong you need to make your walls, your dam walls. Or if you're building a giant aquarium, and you're going to have millions of gallons of water in it, and you're going to have people down below it at a depth, the glass is at a depth of 20, 30 feet below the surface of the water. Well, you need to know how strong that glass surface needs to be, because the last thing you want is people coming and visiting your aquarium and then getting drowned in millions of gallons of water. Not to mention the fish and stuff that are in your tank aren't going to be very happy either. And so in the next video, we'll look at an example of actually computing one of these force and pressure situations.